Hi, I'm David Bourne. I'm a principal scientist at the Robotics Institute, Carnegie Mellon University, and we've been the PI on one of the iFAB programs. The future is to build custom vehicles or near custom vehicles fast and well. Manufacturing is the key. We need to identify, decompose the design into manufacturable components and make them 5 times faster than previously possible. First, we need a series of programs called a tool chain or a digital thread, and these programs basically extract the components of the design, build an electronic bill of materials, break the entire design into sub-assemblies where each of the sub-assemblies can be produced rapidly, and some of the components will also be bought offline.
So a priori also does manufacturability analysis. So here we select side milling, and so it's looking at these two faces to see if they can be manufactured with side milling. And so if you notice, this red X is showing you, it'll explain that it has a 0 radius corner and it can't be made with side milling. So that feedback we can give to the meta designer. So meta designers are going to be submitting lots of parts, and so a priori can bulk cost multiple parts at once.
The inputs to this tool through the EBOM are the key characteristic dimensions, which are the imported dimensions of the final product, as well as the mating constraints between the parts.
Our assembly planning system takes a 3D assembly as input and generates a feasible assembly sequence. We have also developed a motion planning API which provides function calls that can be used to determine motion feasibility of parts on a factory floor.
Sub-assemblies are identified, the components are extracted from the sub-assemblies, and kits are built. These kits are then either outsourced or built in the foundry, then rapidly assembled. As the suppliers deliver them, they're delivered just in time.
We've taken the spirit of innovation and this drive to be fast, flexible, and adaptive and translated it to defense applications. The race in defense is to support the warfighter and bring them home safely. We do this by providing advanced technologies to markedly improve the performance of what's currently available. We are designing and developing the next generation of military ground vehicles. We are exceptionally good at what we do, and we do it really fast.
Our frames are currently designed and built for hand manufacturing using the highest skilled labor, craftsmanship level, quality. And DARPA iFAB is really pushing us to automate some of those processes. We see an opportunity with the DARPA iFAB program to better our business, to make us more efficient in what we do.
A key element to rapid setups is the ability to use augmented reality. This is a new technology that's very exciting. The robot can basically direct the human operator to locate fixtures and components at precise locations. This is actually very difficult for the human operator and something very easy for the robot. My gosh, we should have the robot doing the location of these elements, and we should have the person doing the manipulation. The key to cost-efficient custom manufacturing is rapid setup. The time is all spent setting up the manufacturing process. Literally 98% of the time is spent setting up. So if you want to make a dramatic improvement in time, you better be focused on how to improve the setup time. The robot and the human operator are working collaboratively. The robot is carefully instructing the human where to put fixtures, where to put components, and the robot can then rapidly do the welding process. So the game here is changing. The game is changing to the point where we're trying to make things rapidly and not totally automate everything, but do what's best for the robot or do what's best for the human operator or have them work together as a team. We've augmented the robot with 2 unusual tools. It has a projector for augmented reality, but it also has a laser displacement sensor. The red spot shown here is in fact taking a measurement, and this generates a point cloud that can be used to reconstruct the entire working environment. Once the space frame has been produced, now the mechanical assembly process starts. The University of Maryland has actually worked on a tool to determine an automated assembly sequence. At the same time, we start to see closure at this level back to the design, which is fascinating.
At each partition, kinematic analysis of over-constraining as well as adjustability is employed, and that gives a hint as to how well variations can happen in the final product.
When I think of the relevancy of manufacturing in American culture, where it has been, where it is, and where it's going, I think AVM has an incredible potential to move us in the right direction.